Okay, we're going to talk about exponential and logarithmic equations now. These, of course, are going to be solving equations here. So the videos we've been focusing so far on exponential and logarithmic equations, we've been primarily focusing on what exponential equations are, or exponential functions, and then kind of the domain and range, and then we talked about logarithms and talked about how we could use log properties to rewrite things. Now we're actually going to start talking about solving exponential equations. So the reason we want to talk about solving exponential equations, a quick example you could ask yourself, and maybe we'll even do this as an example of a first problem here. So let's even do kind of we invest. Let's do again $1,000 at, let's go ahead and do 7% APR compounded monthly. How long does it take for the money to double? So we're going to see how long does it take for this to double. So now remember, our compound interest formula was P is equal to A 1 plus R over N to the N times T power. Now, unlike some of the other problems here, what we're actually going to be solving for is we're going to be solving for T. So that's a whole different process here than what we've been doing before. We haven't ever solved for the variable when the variable's in the exponent. Now, that can kind of give you right away why we want logarithms, because what do logarithms give me? Remember the first thing we said that logarithms give us, they give us exponents. So if I'm looking for something in an exponent, we know that logarithms are going to have to take place in this problem because I'm trying to find an exponent. All right, but now let's plug in some things that we know here. What do we know? Well, we actually know P, we know what P is. P is 2,000 because I'm saying that the money is going to double. So I initially invested 1,000 and I want to see how long is it going to take to get to be 2,000. So I have 2,000 is equal to, well, my initial amount was 1,000 and then 1 plus R, which is 7%, so 0.07, divided by 12. And I think I might change this number here just to make things a little bit nicer computational wise, and I think I'm going to here. Let's change this 7 to an 8 here. That'll just make things, I think, a little bit nicer for us. So actually, not 8. I think it's 9 that I want. Let me just, yeah, 9. So let's change this to 9%. And the only reason I'm doing that is it doesn't change any of the way we're going to solve the equation or the problem. It just makes the numbers a little bit nicer that we're going to deal with here, so that there's not as big of decimal numbers that we have to deal with. That's the only reason I did that. And then of course n is still 12, so this would be 12t. So let's go ahead and write this. This would be 2,000 is equal to 1,000, and then 1 plus 0.09 divided by 12 is 1.0075. See, that's kind of, again, why I did the 0.09 there. So we have a decimal that actually ends here, as opposed to repeating forever, to the 12t power. Now I'm going to solve for t. So first thing, and you might guess this because you might see that, well, hey, look, this is multiplication, 1,000. So I'm going to actually divide both sides by 1,000. So divide both sides by 1,000. And then, of course, on the left-hand side, I'd just be left with 2 is equal to 1.0075 to the 12 times t power. Now, what do we do at this point here? Well, think of this. This is my base here is a. Now, I don't want to do a logarithm of 1.0075 as the base, but I'm going to do a logarithm of both sides. Because remember, kind of with equalities, the general rule of thumb has always been as long as I do it to both sides of the equation, I don't change the fact that the equations are equal to each other. So as long as I do the same thing to both sides of the equation, I should be fine. So now we have two logarithms, natural log or common log, but with the change of base formula, we should know that it doesn't matter which one we use, and it doesn't matter in this case. You could go ahead and use the common log to verify that we get the same answer. I'm going to, of course, use the one that I tend to always use, which is natural log. So I'd have natural log of 2 is equal to the natural log of 1.075, not 1.0075 to the 12t power. Now you might say, how is this helping me solve it all? Well, now this is where we use properties of logarithms. Remember, you have a power property. So what can I do to this exponent right here? That exponent I can bring down in front and write it in front. So what would I have? I would have that the natural log of 2 is equal to 12t times the natural log of 1.0075. And then what do I get here? Well, I'd have that the natural log of 2 divided by the natural log of 1.0075 is equal to 12 times t. Now if you wanted to start plugging things in, you could. I would personally just divide by 12 and then do it all at once. But let's go ahead and write what this is. So natural log of 2 divided by the natural log of 1.0075. And if you get this here, you get 92.765, and then I'll round 8, is approximately 12t. It's not going to be exact, but it's going to be good enough for us because we're really wanting to know roughly how many years. And so, having 4 decimal spots, if we're talking about number of years, that's going to be pretty accurate for us still. So divide both sides by 12. And we get that t, again, is equal to, now I'm going to round it, 7.73 years. And it would be okay to write 7.73. It is compounded monthly. So 7.73 is roughly 7.75, so you could think about it as 7 years and 9 months. So almost 8 years before your money would double. Which actually is not an unrealistic thing if you're talking about retirement accounts. Now, if you're talking about a savings account will never have an interest rate of 9%. But retirement accounts, you can sometimes, if you're investing wisely and everything, you can get sometimes returns of up to 9% or even a little bit higher. There's been a couple years where I've had some returns that have been like in the 12 to 15% range. Now, it doesn't stay that way every year, it changes every year, but it's not unrealistic. All right, let's look at a couple other equations here, solving equations, exponential ones. So let's go ahead and look at 10, whoops, I like the black, 10 to the 3x is equal to 12. Now this one is a lot simpler. In fact, we started, quite frankly, with one of the most difficult types of examples. So if you understood the first problem, all of these rest of them should be pretty straightforward for us. Okay, so how are we going to do this here? Well, 10 to the 3x is equal to 12. Now, as I said, it doesn't matter what logarithm you use. However, you do want to use your head when you're doing this. 10 is the base of my exponent here. Well, we have 2 logarithms on the calculator. One's the common log, one's the natural log. So what's the base of the common log? The base of the common log is 10. So really, we want to use the common log in this problem. So you'd have log of 10 to the 3x is equal to the log of 12. And so using the properties here, 3x is equal to 3x times the log of 10 is equal to the log of 12. Now you could go ahead and divide that both sides, but just go ahead and compute what the log of 10 is. And if you compute what the log of 10 is, you'd get that it's 1. And that's because what's the base of the common log? It's 10. So we have 3x times 1 is equal to the log of 12, which of course just dividing both sides by 3 gets you x is equal to the log of 12 divided by 3, which of course is the exact answer. And then if we wanted to get a decimal approximation, we would just do the decimal approximation. So we have log of 12 divided by 3, which would be 0.3597 approximately. Now, I just want to put off to the side here, you could have done this with natural logs, you still would have gotten the same answer. If you had 10 to the 3x is equal to 12, and you did the natural log of both sides, well, you'd still get this 3x coming out in front, times the natural log of 10, natural log of 12. Oh, what's going on here? There we go. But this time, natural log of 10 isn't 1, so you get 3x is equal to the natural log of 12 over the natural log of 10. And then you get x is equal to the natural log of 12 divided by 3 times the natural log of 10. Now, if you, not 0, 10. If you do this on your calculator, you'll get the exact same answer. Now, as far as what is acceptable on an exam, well, if you're asking for an exact answer, this is the one I would want us to do. And the reason being is that there's only a single logarithm here where we have two logarithms here. So this problem kind of illustrates, well, which logarithm should you use? So which logarithm should you use when solving exponential equations? And there's a pretty short answer to this. So we have a to the x, for instance, so you have some base. If a is equal to 10, use common log. Rhythm. So log base 10, or just log. If a is equal to e, remember e is my natural exponent, then use the natural logarithm. So this would be ln. And then if a is equal to, or a is not equal to e, and a is not equal to 10, use either one. Meaning, use either the log or the natural log. It doesn't matter at that point because you're going to have two logarithms regardless of what you do. Alright, so let's go back and look at one or two more examples here. Let's look at this one here. So we have 8 times e to the 6 minus x power is equal to 40. So we're going to, of course, divide both sides by 8. So we'll start off by dividing both sides by 8. Because you're really wanting to get your exponential portion by itself. So then we'd have e to the 6 minus x. Well, 40 divided by 8, if I can do my arithmetic correctly, would be 5. And so what do I do next here? Well, next I'm going to have to do a logarithm of both sides. And if I do a logarithm of both sides, what should I do here? Which one should I do? Well, I have a base of e, so I should do a natural logarithm. So I'm going to do the natural log of e to the 6 minus x equals the natural log of 5. Now, here, there's two ways to approach this. I'm going to kind of write one way here. One way is to use your power property, and you have 6 minus x natural log of e is equal to natural log of 5. But there's another way to think about this, and this is dealing when we talked about inverse functions. When we first defined the logarithms, if you have the log base a of a, and I'm just going to put z here, this is just equal to z. The other one you can do is if you have a to the log base a of z, this is equal to z. These right here, these properties, which we already know, but these are called inverse properties. And so really we could just skip from this line and go down to, and writing this as 6 minus x equals the natural log of 5. Because if you do the natural log of both sides, natural log of e, you can do it in your calculator, but this here is just going to be 1. So you can write this red step down and then go down to the blue step, or you can just go from this black line here down to the blue line. And if you're doing this black line down to the blue line, what you're using are these inverse properties here. Alright, so let's finish solving this out. So it's not much left to do here. I'm just going to go ahead and add x to both sides. So I'd have 6 is equal to the natural log of 5 plus x, and then I'll subtract the natural log from both sides. So you have 6 minus natural log of 5 is equal to x. Now, one thing you don't want to be tempted here is sometimes people are like, oh look, it's subtraction, I can apply my logarithm properties. You can't, because this is not the logarithm of 6, it's just 6. So this is my exact answer here. So this is the exact answer, and you need to read the directions on these problems when you're doing homework problems or on the exam, if we're looking for exact answers or decimal answers. And if we say decimal answers, we will in general put down how many decimal points we want those answers to. Okay, 6 minus the natural log of 5, if we did do that for a decimal, you get that this is approximately, x is approximately 4.3906. Typically I do 4 decimal spots. In general, when you're talking about real life scenarios or using these things in other courses like physics courses or chemistry courses, the reality is the number of decimal points you carry is governed by the significant digits on the problem. Now if you don't know what significant digits are, that's something that again is primarily used in physics and chemistry courses or other science and engineering courses. Alright, I want to do one more example of exponential equations, because this particular one tends to throw people off a little bit. They get a little confused by it. And so let's look at this here. We have e to the 2x minus 5e to the x plus 6 equals 0. Now, this has a challenge here because I don't have a single exponent. I've got 2 exponents. I've got e to the 2x and e to the x, and there's no way to combine these two things together. However, there is a little sneaky thing you can do here, remembering exponent properties, that e to the 2x you could write as e to the x quantity squared. Because what do you do to these exponents? You multiply them. So x times 2 would just be 2x. And then minus 5, and I'll go ahead and put this in parentheses, e to the x plus 6 equals 0. Now, remember when we talked about quadratic types of equations? Well, this is a quadratic type of equation. Why is it quadratic type? I've got something squared, something to the first power, and then just a constant. So what you can do is, for this I'll just say, let's let y equal e to the x. So if I substitute then in, I would have y squared minus 5y plus 6 equals 0. Well, I can now solve this equation for y. That's pretty straightforward to do. I was going to say my thing's not scrolling up here. Because this factors, and this would factor to y minus 3, y minus 2 equals 0. And then, of course, this is just y is equal to 3 or y is equal to 2. Now, of course, this isn't my final answer because what do I know? Y is equal to e to the x, and I'm wanting to solve for x. So what do I have here? I have that 3 equals e to the x or 2 equals e to the x. And then applying the correct logarithm, which in this case would be the natural log of 3 is equal to the natural log of e to the x, or the natural log of 2 is equal to the natural log of e to the x, which gets us the exact answers of x equals the natural log of 3, or x is equal to the natural log of 2. And of course we could do these as approximate, so x is approximately 1.0986, or x is approximately 0.6931. So a little bit tricky there, I think, but just to kind of scroll back up here, when you have e to the 2x, you want to remember that you can have e to the 2x as e to the x quantity squared. And then this would be a quadratic type of equation that you're looking at. Alright, so we've just done examples of exponential equations, so as you might guess, in the next video here we're going to talk about logarithmic equations.